Please label these notes Antiderivatives 5 Notes, Tricky Antiderivatives, and write today's date. By the end of this lesson, you should be able to take antiderivatives for particularly tricky functions. So there are a couple of things that can make antiderivatives tricky, aside from just that finding U-substitution can be hard to do. One is notation that's unclear or unfamiliar. And there are a couple of ways that'll tend to happen. This is the most common one. The antiderivative dx over 3x plus 1. Now all this is that this dx has been treated like a variable. And what this really means is it's the antiderivative of 1 over 3x plus 1 dx, as if we just sort of multiplied across in the numerator and denominator as dx over 1 and sort of merged them together. So if you ever see this pattern, this is all it means. So when we do that, we have a box function here, 1 over something. So we'll let our u equal 3x plus 1, du dx equals 3, du over 3 equals dx. We'll substitute in with that, so we have the antiderivative of 1 over u, du over 3. This 3 comes out to be 1/3. The antiderivative of 1 over u is the natural log of u plus c. And then we put our u back in. And there we go. So once we know what this looks like, it's not so bad. Check our work as always. The 1/3's along for the ride. The derivative of natural log is 1 over 3x plus 1. And then we have to take the derivative of what's inside, which is 3. So those cancel out. We end up back where we started. Another way that these can be tricky is if they're using different variables. So for example, let's take the antiderivative of 4t cubed secant squared t to the 4th dt. Instead of our dx, we've just got that t there, which sometimes throws people off. So remember, with one like this, we're going to do a rewrite step because of that squared. So we've got 4t cubed secant of t to the 4th squared dt. And this is one that can be a little tricky to find because we've got one box function right here and another box function right here. And if we take this and let this whole thing be u, the secant t to the 4th, then when we take the derivative, we're going to come up with secant t to the 4th tangent t to the 4th. That's not going to cancel out what's over here. What will cancel out what's over here is if we let this t to the 4th be our box, be our u. This is with respect to t now, not x. So we can substitute. These cancel out, and we just have to remember that the antiderivative of secant squared is tangent. So tangent of u plus c. Put our u back in. And there we are. When we take our derivative with respect to t, derivative of tangent is secant squared of whatever is in the box times the derivative of the box, which is right what we had to start off with. this sort of a different variable isn't too bad. It's what we've seen in previous problems. But here's one that really trips people up. Let's say we have the antiderivative of u squared, u to the third plus 7 to the 9th du. Now, because we do u-substitution, this is one that can really mess people up, because normally we would pick out our box function and say we're going to let this be u, but there's already a u. So, what we have to do is we just have to pick another variable to keep from being confused. Doesn't really matter what that variable is. I'll just go ahead and make it w since I can't use u. So let's say w equals what's in the box, so that's u to the third plus 7. So derivative of w with respect to u is 3u squared. dw is 3u squared over 3u squared equals du. And so I'm going to substitute these in just like I was doing before, but because I've got this u to start off with, I'm going to be converting to a w. U squared, this all equal w to the 9th. This is dw over 3u squared. So we've got 1/3 antiderivative w to the 9th dw. Now that these variables exactly match, we can take the antiderivative, add 1 to the exponent, divide by the new exponent, w to the 10th power over 30 plus c. Now we got to make sure, even though this is not a u, and normally we see when that there's a u that we have to go and substitute back in, we did this substitution, this w substitution instead of this u substitution, so we still have to remember that final step, go back and convert it to the variable we originally started with. So it's u to the third plus 7 to the 10th power over 30 plus c. When we take our derivative, we're going to take our derivative with respect to u. So that's 1/30 times 10 u to the third plus 7 to the 9th times the derivative of u to the third, 3u squared. So 3 times 10 is 30. That cancels out with this. And we have u squared, u to the third plus 7 to the 9th. It's exactly what we should have. There's one final set of tricks. So these are tricky derivatives to recognize. So remember these two rules, that the derivative of secant x is secant x tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. And so when we have a problem like this, antiderivative of x times the cosecant of x squared times the cotangent of x squared dx. We have to sort of look at these and realize that even though there are two things multiplied together right here, these are really all one antiderivative. It's this antiderivative here. The antiderivative of cosecant x cotangent x equals negative cosecant x. And likewise up here, antiderivative of secant x tangent x equals secant x plus c. Can't forget the plus c's. And so when we're looking at this here, we actually have almost like a double vision. We have sort of a double box here. these two are exactly the same thing, and they really are just one set of functions that we're going to take the antiderivative of. So these two are really, really hard to recognize. But when we do encounter them, whatever's inside the cosecant and the cotangent, that should be the same thing, and that's what equals our u. So what we do is we get the antiderivative of x, cosecant u, cotangent u, and then du over 2x. So that x cancels out. Got a 1/2 along for the ride, antiderivative of cosecant u, cotangent u du. Now this exactly matches something that we have a formula for. So all this is going to condense down into negative cosecant u plus c. And now we put our u back in. That's negative 1/2 cosecant x squared plus c. This is one where it's really important to take the derivative to check your work, because that's not an obvious one at all. So the negative 1/2 is along for the ride. The derivative of cosecant is cosecant of whatever times cotangent of whatever, and that's negative. And then times the derivative of x squared, so that's 2x. The 2's cancel out. The negatives become a positive. We have x cosecant x squared, cotangent x squared. Just like we're supposed to. This concludes Antiderivatives 5 notes.